chapter for today, and it's bell-shaped data. And we started off by doing what was called the empirical rule, which is if you know the mean and standard deviation, you can actually build a reasonably accurate diagram of what the data would look like, and even describe certain regions and what percentage of the data was in that. So I'm going to start with that type of question. So I want you to imagine that we collected data on the ages of elephants, and the average age of the elephants was 25, and that their standard deviation was, let's say, 2. And I'm going to use only that data and what's called the empirical rule to discover as much as we possibly can about what this is telling us. Now, we'll assume that the data is bell-shaped, right? So that's just going as an assumption. So one of the first things that you would do or be asked to do might be to create what the histogram would look like. And right in the center, you get the mean, which is 25. And then you go 1 standard deviation, 2 standard deviations, 3 standard deviations by adding 2, adding 2, adding 2. Then you take away 2, then you take away 2, and then you take away 2 more. And I put little lines on these. And basically, I can now answer questions. For instance, is 33 an outlier? I see a nod, which I agree with. Would you agree that anything that lives beyond the 2 extremes, right, which is 3 standard deviations, big or small, these are considered outliers? So that would be yes. But if I went and said to you, is 20 an outlier? The answer would be definitely no. So if you were taught, if this was about elephants, you would be saying, if someone found an elephant and they tagged it and they found out it was 33 years old, wouldn't that be an exceptionally old elephant, right? And if you found an adult elephant that was 20 years old, that wouldn't be exceptional, right? You could find them pretty easily. Now, you can also do questions like, if you take 1 standard deviation away from the mean, so in this case, it's 23-year-old up to 27-year-old. What percentage of elephants are going to be in that age range? Right, 1 standard deviation either side of the mean. Can you remember the rule?
68.
68. Which is why the empirical rule is sometimes called the 68, 95, 99.7. Right? I could, for instance, say to you, if I wanted to phrase the question kind of in a different way, I could say to you, what range is the middle 95% of all ages? Well, 95%, doesn't that mean 2 standard deviations away from the mean? And so your answer, if I asked it that way, what range is that? You would say it's from 21-year-olds to 29-year-olds. So that would be the typical middle 95% of all ages, at least of this case here. Now, if this was real data, I'd be quite worried about the elephant population, because would you agree there's not very many young adults? So this population, if this was real data, would consist of an awful lot of adult, older elephants and not that many young ones, right? And so you would be concerned about birth rate and so on. And that can be done by, overhunting, because if they kill too many of the males, and you realize you don't get as many babies and therefore not as many young, right? And so I'd be worried if that had happened. Now, I use the word range here. I'm going to use a different version of the word range. If I asked you what was the range of the data, don't we just do 6 standard deviations, which in this case would be 12 years. Remember that rule from yesterday? Now, there's one more piece of information you can get from this, and that is maybe the hardest one of them all to do, but I'm going to try and do it anyway. And it would be a question like this one here. What percentage of the data, phrased it wrong, right? What ages is the bottom 5% in? So if you imagine this here as a baby version of that, I want to know what that age there is, so that this piece here is 5%. Let me change that to 2.5%, just to make it a little bit more interesting. Now you might say, well, how can you even figure that out? There's no obvious way. Well, there is a way to do it. So if I go 2 standard deviations away from the mean, right? 2 standard deviations away from the mean, isn't that 95% of the data? Would you agree? Right, the middle 95% is 2 standard deviations away from mean. So that's from the number 21 to 29. Now, if the middle lot is 95, doesn't that mean that these 2 guys are the other 5%? With me so far? And if they are the other 5%, would it seem reasonable that they're the same size because of symmetry? So if you were being asked, what age is the bottom 2.5%? The answer to that question is, 21 years or younger. Suppose I went and said to you then, what age would you have to be in the top 2.5%? Then wouldn't it be 29 years or older? So if you wanted to be in the top 5%, the answer would be 29 years or older. So you can actually use only the fact that you know it's bell-shaped and the mean and standard deviation. You can use it to create this. You can test for outliers. You can tell me what range, 68, the middle 68%. You can actually tell me what the range is. You can even tell me what would you be to be in the bottom 2.5% or the top 2.5%. So I'm going to do another one of these guys with IQs. So we know that the mean of IQs is 100 and that the standard deviation is 10. So this would be 100, 110, 120, 130, 90, 80, and 70. And I'm going to use this guy to find out what IQ do you need to be in the top 16%. Let me check that. Yeah. So the question is, what IQ do you need to be in, right? What's your IQ if you want to be in the top 16%? Now, if you do 1 standard deviation away from the mean, isn't that middle 68%? Agreed? That's what I'm going to start with. Now, that means the other 32 And isn't the other 32 made up of 16 on this side and 16 on that side? So the magic number is there. An IQ of 110 or better. That will make you in the top 16% of IQs. So if you know what your
question.
Yes.
I actually did the homework on this already. I just read in the book. Is it true that anything that says 16% is just the one deviation and then 2.5% is two deviations? Because that's what I found in the homework. Is that always true?
Yes. And it depends if you're in the top or the bottom. So it's 110 if you want to be in the top, but isn't it 90 if you want? Nobody would want to, but if you were in the bottom, it would be 90 or less.
Yes. Is there something for the third deviation, or is it just the 16 and 2.5%?
And the other one is probably not ever going to be a question, because the other one would be in the top 0.035%. I mean, it exists, but I don't think anybody asks you that. Are we good? Right. Let's move on to our next piece of the puzzle. Got my little list so I can make sure I don't miss anything. We are going to be calculating what is called standardized Z-scores. So let me give you a kind of background of why we need these. So I want you to imagine that we have two people, let's say twins. One of them is going to be called Mary, and the other one's going to be called Donald. And Mary was into English, and Donald was into math. Actually, that's one of my sisters. And they did a test one day, and Mary came and she said, "Hey, I got a score in my English test and it was 82. And Donald said, "Well, I got a math test and I got 79%. And Mary went and said, "Well, I did better than you, because I got 82 and you only got 79. And that seems reasonable, doesn't it? That might be evidence that she's right, right? She did better in her English test than you did in your math. But that's not the whole story. If you want to tell how well someone has done relative to the rest of the group, you need to know what kind of test it was like. And what do I mean by that is, how hard was the test? Would you agree if the average in the test was 92, isn't getting a score of 82 quite easy? If the average was 92, a lot of people are going to get that kind of score. On the other hand, if the test, the average was 50, isn't somebody who got 82 exceptionally good, right, in an average? So we need to know two things. We need to know what the typical score. So I'm going to call that 75. And in this class, they also got 75. And so Mary would still say, "Hey, I did better than you, Donald." Right? The average in the class was the same, and I did better. Right? I did better than the average, and I got more than you. You did better than the average, but I did even better than you did, right? That kind of argument. And that's even more convincing, yet it's not the full picture. Because couldn't you get an average of 75 where almost everybody in the class got 75 and just a few people got more? In that case, wouldn't 82 be a really exceptionally good score? Couldn't you get an average of 75, but there was, people were getting 100 and people were getting 40, right? The scores were all over the place. So we also need to know what the standard deviation is. And in this class, the standard deviation was 15. And in the math class, the standard deviation was only 5. So if I did a little histogram of this class, there would be 75, right? And since the standard deviation is quite big, it would look kind of stretched out a little bit. In this class, there's 75, but since the standard deviation was 5, can you see there would be a lot less variation, right? A lot less wiggle room. And then if you put the 82 and the 75, don't you now get a better picture for who is actually done best compared to the other? And that's why we need a thing called a Z-score. Because what a Z-score does is it takes the raw data, right, the score, and it standardizes it so that you're comparing like with like. And to calculate the Z-score, you use the following formula. It's the real data, right, the score you got, take away the mean, divided by the standard deviation. And that we call the Z-score, right? Very often it's just called Z equals, but I like Z-score, so I'm going to use it. So let's check them out. I'm going to get the Z-score for Mary, and then I'm going to calculate the Z-score for Donald. And whoever gets the biggest Z-score is the person who really did the best, right? So that's going to be the winner, the person with the larger of the two Z-scores. So here goes. Let's do Mary first. So it's going to be 82, take away the average, which is 75, divided by 15. So put a little bracket around it so we get the order of calculations right. And she got a Z-score of about 0.47. Right, that's our Z-score. Let's see what Donald did. Well, Donald got a score of 79, take away 75, but the standard deviation was 5. And that came out to be 79, take away 75, which is this guy, divided by 5. And the answer in this case, let's check that, it doesn't look right. 79, take away 75, and then divide that by 5, and I get the answer 0.8. So in fact, Donald did do better than Mary. You might say, but he didn't get a high enough score. She bet, and the average was the same. So what made the difference? The difference is how spread out they are. If you can imagine where 79 would go, wouldn't it be quite near the top scores that people would get in that class, right? And if you put where 82 is, can you see it's good, but there's a lot of people who did more than she did. Can you see visually, that's a harder score to get in this class than getting it in that class, right? So this is where 82 would be in this one, and this is where 79 would be in this one. And standardized Z-scores are used a lot in all sorts of places, but one of the ways that they use them is so that you can fairly compare two different groups, right? Can you imagine I've been told this, I do not know if it's true or not, but a student told me once that he had an English professor at high school who never gave anyone 100% for an essay. You just aren't allowed to get 100%. And the argument for this English professor was nothing is perfect, right? There's no essay that's ever perfect. So 99% is as good as you're going to get, right? Now, can you imagine getting an exam off a professor that had those kind of standards? Couldn't you get 80? But getting 80 is really, really hard to get in his class. And couldn't you get an English professor who's, as long as I can read it and it's vaguely interesting, I'll give you 100. Can you imagine in that second class, wouldn't it be much easier to get a really good score? In fact, getting 80 in that class probably means it wasn't that good an essay, right? So do you see that if you want to compare two things, don't you have to have some way of taking out the differences in averages that sometimes can happen and the differences in how spread out the data is? And so that's the reason that we use them. If you've ever taken an SAT score, an SAT test, do you know that those are standardized? Because some years the questions are a little bit harder than the previous year. And right, it's a bit unfair that you just happen to be born in the year that the hard SAT test was being taken, right? Rather than the easy one. We are good. So I am busily looking for some questions on calculating z-scores, just to show you what they look like in WebAssign so that you don't get too surprised. In fact, I found it, so let me show you what some of the questions you're expected to do. For instance, this one is to do with IQ tests of some kind, yeah. In this case, the mean is 100 and the standard deviation is 15. And can you imagine then that D, you'd put in 100. And then wouldn't this be 1, 2, 3 standard deviations? So this would be, in this case, 115, 130, and then finally 145. So, whoops, put the 5 in. Do you see how WebAssign gets you to draw the picture, right? It just, you know, the way you fill the information in. And basically you've got that guy. And those, you know, those questions, 68%, 99.7, that's what that one looks like. And here we go. The mean is 170 and the standard deviation is 20. Let's find the z-score. So if somebody was 203, you'd go 203, take away the mean, divided by 20. And that's what calculators are for. So that's 33 divided by 20. And I get the answer of 1.65. Are you comfortable about how you could calculate the z-score for any one of these numbers? Wouldn't it be the score, take away the mean, and divide the answer by the standard deviation? Right. And they're not asking you to do any compare and contrast here. Do you see they're only asking you to calculate it? Now, in this story, suppose the amount spent on textbooks was a mean of 540 and a standard deviation of 100. Find out what the standardized z-scores, right? The z-scores for these numbers are. So for instance, if I was doing 500 and I wanted to find out what its z-score is, it's 500, the score, take away 540, the mean, and divided by 100. And that ends up being equal to negative 0.4. And z-scores can be negative. If I tell you that the z-score of something is negative, doesn't that mean that they got less than the average? Smaller than the average, right? Your score, take away the mean, divided by standard deviation. So in fact, shouldn't half the z-scores be negative and half the z-scores should be positive, right? Half the numbers you get are less than the mean, half the numbers you probably are going to get are more than the mean. Here's a different question. I'm just using these boxes to type. There's nothing to do with the question. Suppose I had a z-score and it was 7.2. Right? Suppose I, got a score and the z-score was 7.2. Wouldn't that be an outlier? In fact, wouldn't a z-score of 3.1 be an outlier? Remember, an outlier is more than 3 standard deviations away from the mean. Your z-score is actually measuring how many standard deviations away from the mean you are. So if you have a z-score of 3, it means that you are 3 standard deviations away from mean. So now we have another test for an outlier. Find the z-score. If it's bigger than 3, it's an outlier. If it's less than -3, it's an outlier. Right? So we now have a test. Am I an outlier? Right. I don't know if somebody is an outlier. Let's pick this one, 840. 840 has a z-score of 840, take away 540, divided by 100. And the answer I get here is 3. Whoa, that was annoying. The answer was 3. Is that going to count as an outlier? I mean, it's right on the borderline. What do you think you do? I'm going to tell you the rule, but if you were making up the rule, what would you do?
I'll just say 3 or more.
Right, so in your case, you would say 3 or more. Agreed? That's what I'm hearing. Right. So if you have a z-score 3 or more, you're an outlier. Nothing wrong with that rule. I bet you'll get textbooks that use that rule. But I think WebAssign, or at least this textbook, uses the rule, it has to be more than 3. So 3.0001, you're an outlier, but we'll give you the benefit of the doubt, right? Yeah, you're darn close, but we'll call it good, right? You're still okay. So greater than 3 will be your outlier. Are you good with those questions? So if I gave you a mean and standard deviation and I asked you to calculate its z-score, would you be comfortable with that? Okay. Now, the next one, make this a little bit bigger so we can maybe read it. If you learn that your score on an exam was 75 and that the mean was 67, right? Okay. Would you be more satisfied if the standard deviation was 4 or if it was 15? What would you like to be true so that you can say, I did good? So you got 75 and the mean was 67, and you want to say, that's a pretty decent score to get in this class. Would you want a standard deviation of 4 or 15?
4.
I agree. What's your thinking for why you chose that?
Because there's less students who made it. I mean, the standard deviation is a lot smaller, so you can only get so much higher.
Right. There's not a lot of wiggle room, right?
Yeah.
When the standard deviation is 4, you're pretty much, most people are going to be pretty, close to the mean. Right. Now, I'm going to leave this for a second and show you the last thing that we need to do. And it involves z-scores. And that is asking this question. How unusual is a particular z-score? So if you imagine what z-scores were looking like, I'll tell you what happens. Can you imagine that you took a whole load of data, right? People's IQs. Blah, 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 right? If you turned all of these things, all of these IQs into z-scores, and this one, for instance, would give you a z-score of 0. This one here would give you a z-score of -0.27. This one would give you a z-score of +1. If you took all your data and you converted it into z-scores, and then you used those z-scores to build a histogram, you would get a guy that looked like this. Why is the middle of the hill at 0? Why is a z-score of 0 the same place that the mean would be? the IQ is 100, average, and the standard deviation in this particular story is 10. Why would 0 be the most likely place? So if you imagine this is what the IQs looked like when you did them with the raw data, right? That guy. Okay.
It's the most average and they're not deviating as much as either other side.
That's an interesting way of phrasing it. For an IQ of 100, since the mean is 100 and the standard deviation is 10, won't an IQ of 100 be a z-score of 0? Right. That makes sense? Now, when you do one of these pictures where you take everybody's data, you recalculate it as z-scores, you end up with a bell-shaped curve, right? And this is the z-scores we're looking at, and it looks like this. So when someone says, how do you find out how unusual a particular z-score is? You're really looking at this guy. And he has a very, very interesting set of information. The mean of all the z-scores is 0. So all the pluses get cancelled out by all the negatives. And what you're less likely to be able to understand, because it doesn't have any why should this be the case, do you know that the standard deviation ends up being 1? So back to my question, I'm slowly getting to answering it. How unusual is a particular z-score? So what we're going to do here is we're going to find the proportion of z-scores that are, well, let's say, greater than that one. So they're greater than the given z-score. So I could ask you, or I could phrase the question like this. What proportion of z-scores are greater than 2.1? Right, so wouldn't that tell you how unusual getting a z-score of 2.1 is if only 2% of z-scores were that or bigger, right? We are going to use SALT to answer what percentage of z-scores are greater than 2.1. It's going to be my first one. What proportion of z-scores are less than negative 0.9? And the third one is what proportion of z-scores are between 2 and 3. Now, all of these and any other ones you could possibly want fall inside, can all be done inside SALT. So zooming over to SALT, and I'm going to show you how we do it. There's only one question that involves this, and the one I'm doing right now is z-scores, and then the second one I'll be doing will be with this data. So I'm just going to hit the SALT button. Right. Now, when you hit the SALT button, you'll be automatically taken to this part of SALT, right? So you don't need to actually pick it, but if for some reason it's not there, choose the one that's called distribution calculator, right? That one, right? If for some reason it doesn't appear. Now, make sure that says normal distribution. Isn't that one of the other names for a bell-shaped, right? Bell-shaped, symmetric, normal. Mean of 0, standard deviation of 1. That's what you use when there's z-scores. And I want to be greater than 2.1. Now, if you look at this little picture, do you see that that's actually telling you less, right, to the left? So if you want greater than, you hit this thing called right tail. And I want it to be greater than 2.1. And the little picture down here moves it. And what we have, there's the answer. The chances that you can have a z-score greater than 2.1, right? Greater than 2.1 is this answer here. It's 0.01786 and some other stuff. Now, the second question I wanted was, what proportion of z-scores are less than negative 0.9? Okay, which one of these guys here do you think you're going to use to find less than? Which one? Left tail, right tail for less than?
Left.
Would it be the left?
Left.
It'd be the left. This is an easy way to remember. Left is less, right? L and L. Left is less. So I want it to be less than, and in this question, I want it to be less than negative 0.9, because that's what the question is. And the answer you get is about 0.184 and some other digits. And then the third one that I said was, what percentage of z-scores are between 2 and negative 2? I actually know the answer to this. It's 95%, which is 0.95. Because aren't z-scores how many standard deviations from the mean? So if you go 2 and negative 2, aren't you going 2 either side? So this should be 95 or thereabouts. Both tails? Nope. Between. And on this side, negative 2. And the other side, 2. And would you agree that that's pretty darn close to 95%? 0.9545. So let's show you my answers that I've now got. What percentage of z-scores are bigger than 2.1, which is that? And that is a proportion. Me personally, I like percentages. And for some reason, they make more sense to me. Only 1.8% of all z-scores are greater than 2.1. So if you find somebody's z-score, right, and they're bigger than that number, can you see that they are well up there in really good score, right? A 2.1 or better is a really good score, right? You're in what, the top 2% of the class, right? Now, less than negative 0.19, that's about what, 18.4%? Well, you know, that negative z-score or worse, there's what, 18% of the people are going to have it. It's not great, but would you agree you're not the last person in the class either, right? You know, there's people going to do worse than you, right? You're beating 18.4% of them. Now, if you do this one, it's 95, at least to the nearest whole number. So that's what I'm going to call it. Do you wonder where that 68, 95, 99.7 came from? Yeah, it came from here. If I did between 1 and between negative 1 and 1, do you know I would get 68%? If I do negative 3 to 3, I would get 99.7%. So remember the rule that we talked about? It came from salt. 1 standard deviation is z minus 1 and 1. 2 standard deviation is z negative 2 and 2. And 3 is the other one. Now, the question that you've got to do is the same thing, but with an extra little part to it. Now, I'm going to have to find the damn question because it's disappeared on me. Come on. Here we go. Found it. Yeah. Close this fella off for a minute. And here we go. Now, in these questions, we have to find proportions falling below a specified z-score. So, where are we? The proportion of SAT scores that fall below 470 when the average SAT score is 500 and the standard deviation is 100. So we are going to find the z-score for 480 and the approximate proportion that got that score or less. So you're going to have to, I know it's me moving around a little bit, but there's a kind of method to my madness. Here goes, 470. Normal distribution. The SAT had a mean of 500. And the SAT had a standard deviation of 100. Do you see in this case then we put in the mean and standard deviation of the question. Now we want to get less than 470 people, right? So what's the chances that you get an SAT score less than 470? Well, the z-score for that is -0.3 and the proportion is about 38%. So if I just copy that, there's my proportion. Now, since they want the answer to 4 decimal places, right, so about 38% of the people who take the SAT will get a score 470 or less. Now, what about, what's the proportion of boys with heights below 37 inches? And the mean this time is 34 and the standard deviation is 1. So we want to get below 37 inches and the mean is 34 and the standard deviation is 1. So bring this guy over. The mean is 34. Standard deviation is 1. What is the percentage of them that get less than 37 inches? Is it less than? Yeah, below. Wow. The z-score is 3, and wouldn't that be almost everybody in this group? 99.86, right? 99.86% is pretty much everybody. So you could almost guarantee that in this particular story, the group of boys that you're talking about, almost every single one of them is going to be less than 37 inches or 37 or less. Are you comfortable about how you can use this? There's the mean, there's the standard deviation, and this is the number you're going to see what it's less than. Are we good with that? Because we're running short of time, so hopefully you are. Right. Let's talk about a couple of puzzle questions. The scores in a final exam happened to be bell-shaped. The mean was 71, and the highest score was 100, and the lowest score was 40. Find the value for the range. Don't you just take biggest away from smallest and you got 60, right? 100, take away 40. How can you use that information to estimate the standard deviation? And remember the standard deviation. Remember the range formula? The range was 6 times the standard deviation. Remember we did that? The range of data is 6 times the standard deviation. If I tell you the range is 60, then what's the standard deviation?
10.
10. Did you see what you did there? Just divide the range by 6, and that's a rough estimate. Right. It's not a great estimate, but it's pretty close. So if you have a whole load of data and you just want to kind of rule of thumb, you know, what's the standard deviation going to look like? Couldn't you just take the biggest, take away the smallest, and divide it by 6? Right. Now, the last puzzle question. Head circumferences on some men have a bell-shaped distribution. At least they're not talking about the shape of their head. And the mean is 54 and the standard deviation is 3. What is the variance of the head circumference? We only did variance once. Can you remember how you get the variance? And I'll give you a clue. It uses only the standard deviation number, which in this case is 3. How do you get the variance?
Standard deviation squared.
Yeah, nailed it. So 3 squared is 9. Yeah, isn't it little things like that you want to put down in a little note somewhere? Variance is standard deviation squared. Range is 6 times the standard deviation. Standard deviation is the range divided by 6. You know, little things like that, because they pop in now and again. And we are done.